This means that the core contracts, and the contraction can switch on nuclear burning, like oxygen, neon, even silicon, and this can seriously perturb the evolution of the star. If the mass of the helium core, the central core, is between roughly 60 and 130 solar masses, then this pair instability can lead to the complete disruption of the star, leading to no remnant. If the mass of the helium core is larger than that, then the gravity of the star is so strong that probably not even the pair instability can disrupt the star, and the star may be able to collapse to a black hole directly. And things happen quite interesting even if the mass of the helium core is a bit lower, between 30 and 60 solar masses. In that case, the contraction of the core triggers some additional nuclear burning, which then makes the core expand again, and the stars can undergo one or more oscillations. During these oscillations, mass loss is enhanced, and in the end, the star can find a new equilibrium and can avoid the pair instability region. But of course, its final mass will be smaller. So if we include this kind of models for pair instability, and let me say that unlike core collapse supernovae, we have a better theoretical understanding of pair instability. So if we include pair instability in our model, what we get is something like this. This is again the mass of the compact object as a function of the 0H main sequence mass of the star for different metallicities. And now we consider stellar evolution, core collapse supernovae, and also pair instability. And you see that the features of pair instability are quite important. First of all, there is a region here where there is no remnant left, and this region depends, of course, on metallicity because the mass of the core depends on metallicity. And this region is where pair instability is completely efficient and a pair instability supernova happens. Then there is a region here where if you are able to form stars with mass larger than 200 and something solar masses and very low metallicity. Yes, please?
So I'm not in the screen. Could you just briefly tell us what do you mean by modeling? Do you run a simulation? Do you assume everything's spherical, nothing rotating?
Oh, basically this is close to just population synthesis. So we keep stellar evolution model. In that case, it's one stellar evolution model, but then we check many different stellar evolution models. What it tells us about the evolution of the mass and the core and the radius with time. We had a prescription for core collapse supernova. We checked with another prescription. We had a prescription for pair instability, which comes from here. So it's very simple. It's terribly simple. I think there is another question.
Yeah, I was actually wondering, so you predict the variability gap, you say, and you program it in, I think, between 60 and 120 solar masses, right?
Yeah.
Then the models that you predict, they go up all the way to the first masses over the variability gap are like 160 to 200 solar masses. Why are they so much higher than 120? Is that just low number statistics, or?
Sorry, I'm not sure I got your question. So could you please repeat?
Okay, yeah. So you predict,
these are single stars, right?
Yeah, could you please let her repeat the question, because I'm rather down when I didn't get it.
Oh, okay. I think I got it a little bit, but I was just asking, like, you have the gap indicated between 60 and 120 solar masses?
Yeah, the gap of the black hole masses.
Yes,
right.
of the black hole masses. But then the first models that go above?
There is this one, you see.
Ah,
Yeah.
oh, I didn't see that one either.
Yeah, me neither. The first time they showed me this plot, and also the second time I missed it.
Okay.
Oh, now I learn. No.
So you do.
Yeah, but I can tell you really that this is very uncertain. I will get back to this later because it strongly depends on the stellar model. So if you have these very massive stars somewhere in the universe, and we don't know, with a very low metallicity, then they should collapse to a black hole directly and leave a black hole that is an intermediate mass black hole with mass larger than 100 solar masses. But there is also another difference, which is more subtle but very important in this region here. if you look at this plot, the mass of the compact object here is between 60 and, let's say, 80 solar masses, while here the maximum mass is about 60 solar masses. And this is where pulsational peri-instability happens, and it reduces the mass of the compact object. So the most important feature, I think, because it is something that is observable, of the impact of peri-instability on the mass of compact object is that peri-instability opens this mass gap, which is approximately between 50, 65 solar masses and 120 or so solar masses. Let me say that the actual boundaries of peri-instability are quite uncertain because they critically depend on detail, not only on peri-instability, but especially on stellar evolution models. For example, one of the things we didn't consider here is that real-life stars rotate. These stars do not rotate. And if we add rotation to the whole picture, we get something more like this. So this is again the mass of the compact objects versus the sun's mass. Here is for fixed metallicity. I have also different metallicities if you are interested. And the blue line shows what happens with a non-rotating star. So this, if you check, is almost the same as the previous model for the same metallicity, while the black and red line show what happens if the star rotates with 150 and 300 kilometers per second of equatorial velocity, initial equatorial velocity. And the main thing that we learn from this kind of plot is that while the maximum realistic mass of a black hole that we can get from a non-rotating model is about 60-something solar masses, while the rotating stars cannot grow black holes much higher than 40-something solar masses. And there are two effects that produce this. One is that rotation induces chemical mixing, and chemical mixing grows larger helium cores, and this means that the minimum Zam's mass to enter peri-instability shifts to the left. So with no rotating model, the peri-instability starts about here, while with rotating model it starts here. And the second thing is that rotation enhances mass loss in stars, and then the entire hydrogen envelope is gone by mass loss, even at this metallicity, which means that here, this very massive black hole comes from the collapse of the entire star, including some hydrogen envelope which is left, while this does not include any hydrogen envelope.
Michela,
Yep.
I've got a couple questions about this. This is actually this is counterintuitive to me. I would have expected the rotation would have given you additional, essentially support the core that actually offsets when you start the pulsations. Is that just wrong, or like is it additional pressure support so you don't collapse and get as high a temperature in the center? Am I just backwards about that, or?
Well,
Because I remember Stan used to say that like you had these things rapidly rotating, you thought you could crank the beginning of the gap to like 60 or 70 solar masses.
I think here we should check actually what is the temperature in this model. If what you say is correct, then this should have a lower temperature.
I think it's right on the main sequence, but when you're so far off,
That
lost
temperature is
momentum,
independent.
Okay.
and by that time it's really good.
Yeah.
And
On the other hand,
Okay.
I would check maybe in the model, but I think Selma is right.
Okay.
That was a
Yeah,
good point. That was a good point.
Yeah.
Yeah.
And the other question I had is you actually, so you model this where you actually retain some of the hydrogen envelope when you have even the pulsations for non-rotating stars?
Well, the pulsations start here. Okay, so here you start digging into the hydrogen envelope because of the pulsation. Well, if you don't mind, we can get back to this by the end of my talk, because in the paper we also consider what happens if we change the core collapse supernova model. Or let me see, because this is an important point, if I can find it now. Okay, here it is. So basically, it is very delicate thing to understand whether the hydrogen envelope collapses or not, because it's loosely bound. So it depends on what you assume for your core collapse again. And that's why we decided in these models to keep the fraction of hydrogen envelope that can collapse as a free parameter to show what is the range of uncertainty. So you see this thin line is almost the same as before and is with 90% of hydrogen envelope that is collapsing. Of course, the hydrogen envelope, not the entire one, but the one that is left when instability starts. And this is what happens if you just collapse the helium core. So yeah, if you assume that only helium collapses, then you get a much narrower difference between the two.
Okay.
And I think it may be quite interesting here to look, for example, at papers by Zuckbold and collaborators where they study actually more on this issue of the hydrogen envelope. I don't think has been settled. So I'm done with the first part of my talk where I just discussed how black holes can form from single stellar evolution and what are the uncertainties. I just like to give you a couple of take-home messages. One is if we want to explain Largo Virgo black holes with stellar evolution, then it is very important to account for metallicity in our picture. Pen instability is very important because it predicts that there is a mass gap in the black hole mass function, and LIGO and Virgo will be able to probe this mass gap soon. We should also take into account the effect that rotation can have on the maximum black hole mass. And maybe the most important thing to say is there are still a plethora of uncertainties which are about the stellar evolution and especially about the physics of core collapse. So this means that there is basically a lot of work to do.
So just curious, does rotation affect the high mass and mass gap?